crazy stuff going on. That's all right. We'll get through it. What questions do you have? Everything good? Just heard Sports Center theme. It's all right. All right. Anyway, last time we went through lots of math things that everybody was excited about. Did lots of calculus last time, right? The big thing that we came up with right at the end was the PMF for a Poisson distribution, which was right there. And we also verified that it really was a PMF using our knowledge of what the Maclaurin series for e to the x looks like. So, like I mentioned before, we really need to have an understanding of what a random variable is counting, what it's measuring, either or, depending on what the situation is, so that we know what distribution to apply to it, right? Hello. No, you're fine. So we've talked about the binomial distribution, which counts number of successes in a certain number of trials. So the number of trials is fixed. We're trying to figure out how many successes happens in that number of trials, versus a geometric distribution that counts number of trials until first success, or a negative binomial that counts number of trials until a certain number of successes. Okay. A Poisson is another counting thing, but it's a number of occurrences during a certain unit interval, and we can define unit interval in lots of different ways. And we'll see that as we go through examples. So Poissons count number of occurrences in a given interval, whatever that interval happens to be. This parameter lambda also needs to be given to you to be able to figure out what that distribution is. So I don't know what this lambda is. We just said it was associated with some lambda. So to get to that point, let's calculate the mean and the variance for this distribution, and then we'll be able to figure out what the lambda parameter is in any particular problem. Okay? All right. So before we do mean, we'll do moment generating function, because we like to collect those two. And then once we have the moment generating function, we can get the mean and the variance. So remember again, by definition, how do we calculate the moment generating function? What is its definition? Good. That's its definition, right? And in this case, our support goes from 0 to infinity, because in any given interval, we could have no occurrences, 1 occurrence, 2 occurrence, 3 occurrence, and so on. So we'll have e to the tx, and then times this lambda to the x over x factorial e to the minus lambda. Pardon me. Again, just like we talked about when we did the PMF, no x is here, right? So we can pull it out in front. I still have the x factorial, but notice that both of these pieces right here have an x power in them, don't they? So how could we combine those two things and write it as something to an x power? Good, lambda e to the t, and then to the x. So as far as this summation is concerned, this x is changing, this x is changing, but that thing's a constant as far as the summation is concerned, right? That is just what it is, correct? So again, remembering what our Maclaurin series for e to the x looks like, which fortunately for me is up here on the screen, over here on the right. Notice the n here is changing, so down here the x is playing the role of the n. What's playing the role of the x? The lambda e to the t, right? So this will be e to the negative lambda, times e to the lambda e to the t, right? Because I'm going to replace the x on the. If my lambda e to the t is playing the role of x on the right, it must also be playing the role of x on the left. And now we can just add our exponents. And after I add the exponents, I'm going to factor out a lambda. And it's e to the lambda, e to the t minus 1 there. So there's our moment generating function for the Poisson. Not bad. Again, we can use the moment generating function to calculate the mean and the variance. Since I've got an exponential function, it might be beneficial to us to use that trick that we did by taking the log of the moment generating function before we differentiate, right? Because if I take the log of this thing, what happens? What do I end up with if I take the log of this thing? Yeah, notice that the log and, that's t up there, the log and the exponentials are inverses of each other, right? So we just end up with the exponent. That's a lot easier to differentiate, isn't it? What do you get when you take the first derivative? It's just lambda e to the t, right? Agree? We also need the second derivative to help us with the variance. We might as well do that now. What is the second derivative? Lambda e to the t. That was super easy, right? That was why I said do the log trick to take the derivative, because the derivatives are really straightforward in this case. How do we use these now to figure out the mean and the variance? Plug in 0 into each of them, right? Well, what do you get when you plug in 0 into the first derivative? You get lambda. What do you get when you plug in 0 into the second derivative? Lambda. So notice that for the Poisson, the mean and the variance are equal to each other. Kind of an interesting little tidbit for a Poisson distribution. Pardon me. By the way, if you have any slant towards statistics in the future, one of the things that you might be interested in doing is trying to decide if something is a certain type of distribution. Okay. A lot of times you're looking at normal distributions, and so there's some characteristics of a sample that might lead you to believe that it's normal. But if you get a sample where the mean and the variance are identical, it might be a Poisson distribution. Okay. So there's little tidbits here that might tell you, hey, by the way, the underlying distribution where we're drawing our data from might be a Poisson distribution, or at least a Poisson distribution would be a good model for it. Okay. So if you do anything that has to do with statistical analysis types of things, you might be interested in, hey, does this particular scenario fit my data that I'm seeing? That's a lot of what statistical analysis does, right? You're trying to use a finite set of data to make inferences about an entire population, whether that's huge and finite or something that's infinite because it's infinitely divisible. Okay. So in any event, like I said, this is a nice property of the Poisson that the mean and the variance are the same. And if you come across a situation where you're collecting some data, that might be a good indication that it's a Poisson distribution if they're close to each other. Okay. All right. In any event, we've got the mean and the variance now. I do want to make sure I remember to remind you that pardon me, I wanted to remind you that when we do this trick for the natural log, that allows us just to plug in 0 into the derivatives to get mean and variance. It doesn't work just for the moment generating function, right? It works for the mean, but when you plug 0 into the second derivative of the moment generating function, you get expected value of x squared, right? Not the variance. Okay. So be careful with that, right? If you don't do this little trick where you're doing the log, it's not the variance you get when you plug it into the second derivative, it's the expected value of x squared. Okay, I just wanted to make sure that we all remembered that, depending on what problems you might see in the future. Hint, hint. Okay. Well, there will be an exam at some point, right? Okay. All right. Can we use this now to do some problems? Because that's my guess is you're probably sick of seeing letters and want to see some numbers. Yes? It's okay to say yes. It's fine. All right. Pardon me. So this one's asking you to start with a Poisson distribution with a mean of 4, and then it's asking you to do these different calculations. Are any of these a direct PMF calculation? No. All of them have to do some sort of a summation, right? A direct PMF calculation would be I take the number in and get x is equal to that value, right? Okay. So I'm going to have to do some sums here, regardless of what happens. In this case, notice that the problem says let x have a Poisson distribution with a mean of 4. So right away, that's telling us what the lambda is. When it's telling you that the mean is 4. So this is your lambda right there. So now we know what the PMF looks like. Plugging that in for lambda, we get 4 to the x over x factorial e to the negative 4. That is our PMF. And again, your support starts at 0, right? For a Poisson distribution, you're counting number of occurrences in some interval, in some fixed length interval. Hello. How are you? Good. So again, x is counting the number of occurrences in a fixed length interval. You may have no occurrences, so make sure that it starts at 0. Just to remind, 0 factorial is equal to what? 1, right? So we're not causing any division by 0 issues, right? It looks like there might be a 0 in the denominator, but remember by definition, 0 factorial is 1. Okay? All right. So in the first one, for part A, what will we need to do? So with the probability that we're between 2 and 5. Okay, yeah, so yep, good. I would have written it the other way, but you're exactly right. Yep, you're doing it the right way. You're doing it the right way. That was why I kind of stopped for a second. Sorry. You counted down and I was counting up. Sorry. All right. I would need to do all 4 of those and add them together, right? You could have also written it as a summation. I could do the summation from x equals 2 to 5, 4 to the x over x factorial, e to the minus 4. You could literally plug the numbers in at this point and write it this way. I'm getting exhausted just writing it all out. Oops. 4. But notice that in each of these, this doesn't change, does it? That e to the negative 4 is the same all the way. So I wrote it out longhand. I could have saved myself a little bit of writing just by sticking an e to the 4th out in front, and then write it as 4 squared over 2 factorial plus 4 cubed over 3 factorial, and then the last 2 terms as well.
You have an extra
I do not. I have a pen. Would a pen be okay? Okay. I mean, there is a pencil part in there, but I don't think it has any lead. The only thing I have. Yeah. Yeah, it's true. That okay? All right. For part B, when the probability that x is greater than or equal to 3, if you were to compute it the way it's listed for us, how would you compute it? What would we need to do to literally the way it's written? What would we need to compute? 3 to infinity, right? I would need to use some sort of infinite series thing to try to be able to do it. That sounds like that would suck a lot. Agreed? Okay. Well, how should we rewrite it instead?
Or 1 minus all those things.
Yep, good. Yep, from 0 and a 1 and a 2. Do it that way. Do 1 minus, basically we do 1 minus the CDF, right? 1 minus the probability is less than or equal to 2. And then again, I could write it using this idea. I would have e to the negative lambda, so negative 4. And then multiply by 4 to the 0 over 0 factorial, 4 to the first over 1 factorial, and 4 squared over 2 factorial. That should might do. It did not. That's why it buzzed. I'm getting like 10,000 emails. I need to turn off my watch. That okay? I believe on your calculator there's also a Poisson CDF button. Yeah. Yeah. So you could have also just used your Poisson CDF button and done it that way. Notice that part C would be exactly in the CDF way, right? It is the probability that x is less than or equal to 3. So you could put that into your calculator and use your Poisson CDF and get it exactly. For us, that would be e to the negative 4. It'd basically be this exact same thing, except not quite, right? Oops. Because there's an extra term in this one. Yeah, it has 3 in it, and the other one doesn't. Yeah, they're all that. Yeah, it looks like they should have been complements, right? Now, here's the thing, which we're gonna hopefully we won't get to today, but we'll definitely get to on Tuesday. When we switch over to continuous, they essentially will be complements of each other, because if you have a continuous distribution, the probability that you actually hit a value exactly is 0. So the 3 wouldn't matter in that case. We'll talk more about that when we get to it. But if it's a continuous distribution, they would essentially be the complements of each other. If you add the 2 probabilities together, you would get 1. Or not quite, because they still have overlap at 3, but the overlap at 3 doesn't give you any probability. So, in any event, let's go back up to part A before we go on to the next problem. We rewrote this one in terms of the CDF, right? If we use a capital F, I could think of that as 1 minus F of 2, right? That's think of the CDF using a capital F. Okay. Can you go back up to this one and write it as a statement with CDFs? I probably wouldn't be asking if the answer was no, right? Okay. If I ignore the 2, how would I write it as a CDF? F of 5, right? We agree? But F of 5 includes what? It includes 5, 4, 3, 2, 1, and 0. So what would I need to do to get rid of the 1 and 0? Subtract F of 1, right? Good. So one of the reasons why I wanted to do this is because this is a technique that we're going to use when we do continuous distributions quite a bit, actually. But now, notice I've got it set up where if you don't want to type in all the stuff with the PDF into your calculator, you can use that Poisson CDF function and be able to just do those two numbers and subtract them. I mentioned last time that a lot of these things are built into Excel because I throw things across the room. Metaphor for how my week's going. Go up here. Let me zoom in a little bit so you can actually see what I'm typing. Oops. Notice that there is a Poisson distribution button on there. Okay, just like before. If we wanted to do part C, where it was x is less than or equal to 3, I would use a 3 for the x. Then you type in what the lambda is, what the mean is, and then you tell it whether or not it's cumulative. So you would use true to say that it's cumulative and get the answer. If we wanted to do it for part A, I would do the Poisson distribution for the cumulative distribution for 5, and then subtract the cumulative distribution for 1, and hit enter and get the answer as well. Which, again, computationally saves you a lot of time, right? Because I don't have to type in every single one on a PDF every single time. All right. Yes, I've got it. Why does it always ask me if I've got it or not? Yes, I understand the concept. Okay. You've got functionality. Thank you. All right. This okay? All right. You seem all super excited about it. So I'm happy to see that. Okay. Let's do the next one here. Okay, ignoring the clause at the beginning of the second sentence there, looking at just the first sentence, what about that would tell you that it's probably a Poisson distribution? Again, part of the problem is figuring out what distribution to use, right? So we need to be able to read the problems and figure out what distribution are they even talking about. So again, ignoring the fact that it literally says use a Poisson distribution, ignoring that. Yeah, Matt. So yeah, it gives us a mean, certainly, right? Yeah, and then it says arrive per hour, right? Remember, Poisson distributions count what? Count occurrences in a given interval, right? And this is telling you mean occurrences in an interval. Okay? So those are our key words in here. Arriving per hour is telling us, hey, I bet this is a Poisson problem. Okay? Now again, we need to investigate more, but that's our clues to start with that we were probably talking about a Poisson. Okay? Now again, they literally say it's a Poisson, okay, but ignoring that part. But then notice the last part says, again, even if this weren't here, if I think about crossing it out, if that part weren't here, I'm calculating a probability of something happening in a given hour. I'm counting occurrences in a given interval. The only thing that we know that counts occurrences in a given interval is a Poisson. Okay? Does that make sense? Okay. I'll erase all of that. All right. What's lambda? 11, right? Good. Okay. So we want 10 more than, it says more than 10. So we want the probability that what is true? X is strictly greater than 10, right? Because it says more than. It doesn't say at least 10. It says more than 10, right? We probably want to do what with that before we start computing? Rewrite it as
less than or equal.
Yeah, less than or equal to 10. Notice in your complement, this one did not include 10. So the complement does include 10, right? I'll write it as a summation, but again, I would anticipate that if you're going to give me a final value, you're going to put it in a calculator and use the CDF function. I would not expect you to type in 11 summands. Okay, that's just stupid. There's literally 0 point in doing that. Okay. What's the PDF look like on the inside of the sum?
11 to the x under x factorial. E to the negative 11.
Good. Probably the most common mistake I see a student do when actually plugging something into a Poisson is put an x here versus the actual lambda. So be careful with that. Why? Well, how many times do you write an e without an x in it? Think about when you're doing problems before this class, right? Usually you write e to the x and go on, right? So it's a very, very easy mistake to make without thinking. So, but remember, this e is a number up in the exponent, not a variable. It doesn't change. Okay. All right. So in any event, at this point, that's what a calculator is for, right? I would not expect you to do any of that by hand by any stretch. One of the reasons why these problems are set up this way isn't necessarily for you to use your calculator to get the CDF, but in the back, I can't use the document camera because it's broken. I'll just have to kind of show you. In the back of your book, which what I mean is at the end of the PDF that you have for your ebook or whatever it is, there is a Poisson table where they have various values of lambda across the top, and then the occurrences down the side, and they have the values for the CDF associated with those things. So in this particular problem, on the very, very last column, they have an 11 for the lambda, and you would scroll down to the 10. I know you can't see it. I'm just kind of pointing at things, and you're like, sure, you're pointing at something in the book, right? On the very, very last column, it says 11. At the very, very bottom here, I see a 10 row. That's the number of occurrences. Scroll all the way across, I see 0.460. So if you didn't have a calculator that did a CDF, this would be 1 minus 0.460, which should match what you get in your calculator if you put it in the CDF. And so then you get 0.54. So the way these are set up in the book, you can do it with a scientific calculator. Well, hell, you can do it with a 4-function calculator, but they would expect you to look it up in a table in that case. I would never expect you to type in 11 things in your calculator and sum it up. Now, if you ever were to take an actuarial exam, the only thing you are allowed is a scientific calculator. And so when they have these kind of problems, you may have to do 2 or 3 summands, but they still wouldn't make you do 11. Any questions on that one? All right, well, let's do another one. We're having so much fun. All right, let's read the problem first and figure out what part we're actually looking for. What thing we're actually looking for. They tell us something about some probabilities. I'm going to ignore that for the time being. They tell us we have a Poisson distribution and they're asking for the variance. Well, what about the Poisson distribution gives you the variance? The lambda, right? The lambda gives you it. Exactly right. So this problem is asking you to figure out what lambda is, right? It says it in a weird way because it says calculate the variance, but it's asking what's lambda. Because in a Poisson distribution, lambda is the variance, all right? So now let's go back up to the first sentence that I ignored. 3 times as likely to file 2 claims as 4. So what kind of an equation can we get out of that? Okay, Yep, so it's 3 times as likely to file 2 as 4. So the probability that x is equal to 2 is 3 times as likely as the probability that x is equal to 4. It's exactly right. Yep. Now we should have enough information here to help us figure out what lambda is. What goes on the left-hand side? E to the negative lambda. Yep, good. Like I said, it's easy just to plug in the x, isn't it? Yes, it just said that. Yep. And on the other side, we would have good, fantastic. That's exactly right. On the other side, similar, just putting 4 in for x, right? Good news is what cancels? Yeah, the e to the minus lambda goes away, right? These go away. And now I have a relatively straightforward problem to solve for lambda, don't I? I can divide both sides by lambda squared. Ordinarily, if you're solving for a variable, dividing both sides by a variable is bad because you don't know if the variable is 0 or not to start with, right? However, is lambda ever going to be 0 in a Poisson distribution? No, not much of a distribution if you have 0 occurrences, right? Okay, so I don't have to worry about dividing by lambda squared here. So I'll get a lambda squared on the right. 4 factorial is 24, right? So if I multiply both sides by 24, divide by 3, I get 8, but there's also a 2 in the denominator, so we get a 4. If I did my arithmetic right, feels like I did it right. I did it slowly enough. I don't think I made a mistake. So what's lambda have to be? 2. And so that's your variance. Good. So sometimes, especially again, notice that this is coming from a sample actuarial exam. Sometimes they'll ask questions in a way that makes it sound like it's asking for something more difficult, where really it's just saying, you've got a Poisson distribution. What do I need to know about the Poisson distribution before I can do anything? I need to know its lambda. I need to know its mean, or I need to know its variance. So it's just asking you to figure out what that has to be. Now, why might you do that? Again, I'm trying to kind of lead into if you take the mathematical statistics course at some point, one of the things that you talk about, or any statistics course, is trying to estimate things, right? That's the whole point of doing statistics is I've got something that I can't possibly know every single detail about. I've got to make some estimates, right? Maybe that is you've got 350 million voting members of the United States population, and you're trying to figure out who they're going to vote for president. You can't possibly go and talk to all 350 million people. You wouldn't necessarily want to go talk to 350 million people. You may not want to talk to 350 people, okay? Right? But the idea then is I'm going to talk to hopefully a representative sample, figure out who they're going to vote for, and then try to say, okay, I anticipate this much of the population is going to vote for this person. Okay? Same idea here. If I think that I can model something with a Poisson distribution, but I don't have the information on the entire population, for whatever reason, I'm going to still need to try to estimate what this lambda is. The best thing that you would have to be able to estimate what that lambda is what the mean of whatever the sample is that you got. It's the only information I have, but I know that the lambda for a Poisson is its mean. So if I take a sample, I'm going to use the mean as my estimate for that parameter. We usually refer to these as parameters. Okay. Anyway, I just wanted to mention that. So even though this problem seems strange and you wouldn't necessarily do that in the real world, totally agree. But again, if I'm going to do some modeling and I need a piece of information about the distribution, I've got to figure out that piece of information first, or at least estimate it. Okay. So that's why I'm harping on it. There's reasons why we study these things, whether or not you want to study them, I suppose. All right. Goodness. Let's see. What do we got? All sorts of weird stuff here. You're given what? You've got number of customers arriving during the morning hours versus number of customers arriving in the afternoon hours. You're told both of them have a Poisson distribution. You are told something about the first moments of both of them. And you're told something about the second moments of both of them. Lots of things that you're given. And then it asks you to calculate the variance of y. Again, just like the previous problem, if it's asking for the variance of y, what value are we looking for? The lambda for the y, right? So it's trying to figure out the lambda for the y. All right, so the first part tells us that x and y are Poisson distributed. Okay, so I know something about what the distribution looks like, but I also know that the mean and the variance for both of them are identical, right? Whatever the lambda is for x, the x distribution, that's the mean and the variance for x. And whatever the lambda is for the y distribution, that's the mean and the variance for the y, right? Okay. So the second statement here says first moment of x, first moment of y. Well, what is the first moment? Mean, right? That is the first moment. So it just says the mean for x is x or 8 less than the mean for y, right? So if I use lambda sub x and lambda sub y, what equation can you make? Good. Yeah, exactly right. The first moment of x is 8 less than the first moment of y. So the mean for x is 8 less than the mean for y. So we just made a statement about that, right? Now, the second one says the second moment of x is 60% of the second moment of y. This one, if I have no idea if anyone is interested in actuarial science at all, but some of you might be taking certification exams in something somewhere on down the road, right? There's certainly teacher licensure, engineering exams, all sorts of certification exams. GRE, if you go to graduate school, all sorts of different things, right? A lot of times, the whole point of the test isn't whether or not you know the materials, whether or not you can read, okay? You know the definitions. This is an example of whether or not you know the definitions. We know in a Poisson distribution that the variance is the same as the parameter. Does the second moment refer to the variance? No. Remember, the second moment is expected value of x squared, right? Not the variance. Right? Okay. So this one we have to write it in terms of the variance, but it's not the variance, right? So we know that generally speaking, I'll write this up to the side. The variance is expected value of x squared plus expected value of x quantity squared, right? Or not plus. Thanks for the look. I appreciate it. Not plus. Minus. That was a great look, though. You're like, what the heck are you talking about? Knew I made some error. It's one. Okay. All right. So this is the second moment. Now, for a Poisson distribution, do we know this and this? If we know the value, do we know this and this? Yeah, they're the same, right? Okay. So I can rewrite this for a Poisson. I can write the second moment is lambda plus lambda squared, and that was where the plus was coming from, because I knew I was going to add it to the other side. All right, I would add the expected value of x quantity squared to the other side, and they're both equal to lambda, right? All right, using this knowledge now, can you give me an equation for statement 3?
Lambda x plus lambda x squared equals 0.6.
Where does the 0.6 go?
Outside of parentheses.
Yeah, outside of where though? For the x or the y?
Out of the y.
Okay, good. Just want to make sure we're all on the same page. 60% of, you're right, good,
And lambda y plus lambda y squared.
good. Now I got 2 equations and 2 unknowns, right? We want lambda sub y, so I don't need the lambda sub x, correct? Okay. So I'll use this equation to solve it for lambda sub x. And then since I know, is it okay that since I know I'm solving for just this one lambda, if I stop writing the sub y and know that I'm solving for the one for y? Because I only need the one of them, right? Okay. All right, so lambda minus 8 plus lambda minus 8 squared equals 0.6 of lambda minus 8 plus lambda minus 8 squared. Oh, it's just lambda. Thank you. That I didn't have to plug in over there. Thank you. That makes life much easier. Now it's just a matter of solving, right? So multiply out on the left-hand side, distribute out on the right-hand side as well. Might be a trickier way to do this and not have to worry, get such nasty things. Let's go ahead and gather everything on one side. We'll subtract over 0.4 lambda squared. And then what is that? Minus 15.4. Nope. It's 14.4 lambda. And a plus a 56.
Minus 15.6.
What did I do?
You get
Oh, yeah. Yep. What did I do? Oh, I added.
There's an extra lambda. in there.
Yeah, there's another variable. 16.6 plus a 1. Yep, I added the 0.6 to it. That was what I did. Sorry. Let's see. Is there anything fancy we can do? It's probably just as easy at this point as using quadratic formula than anything else. No point spending an hour trying to figure out what what it is. Lambda is, what do we get? 15 minus, or plus or minus, square root of 15. My goodness. .6 squared minus 4 times 0.4 times 56 all over 2 times 0.4. Whatever that turns out to be, just trying to discern if we're going to get 2 positive answers or not. It doesn't look like we are, so I'm wondering which one we would. They're both negative. Or how are they both negative?
Unless I put something in wrong.
I wouldn't be
I think they're both positive, right?
I probably, no, I put in positive.
Yeah.
That's what it is. Never mind.
What values did we get?
The square root's 12.4.
Okay. Let me actually get some numbers here. You said this is 12.4 altogether?
Yeah.
Like that? Okay. It probably comes out to be something nice.
So the plus the square root's 35.
Okay.
So
And the other one's 4? Is what you said? Okay. Now the question is, do they both make sense? Now if lambda sub y was 4, what would be lambda sub x? -4. Does lambda sub x being -4 make any sense? No, because again, that's a mean number of occurrences of something, right? So it can't be the 4, so it has to be the 35. Yeah. So if I use this one, remember this is for the y, right? So if this is 4, lambda sub x would be -4, and that's a mean number of occurrences for a plus, and that doesn't make any sense because the smallest number of occurrences you could have is 0. So that's why the 4 doesn't work. That'll require a little extra thought at the end. But is the process okay? I know it's a little ugly as far as the algebra went. Yeah, let's do another one. We're having fun. Work on this one for a minute. It's another one of those expected payout type of things. Work on it for a minute and then we'll chat. Pardon me. At least try to get set up what you're trying to do, and then actually computing it might be a fun exercise in the Maclaurin series. Want to just chat? Okay. Are we okay with the PMF? They tell us a Poisson with a mean of 1.5, so that's the lambda. So that would be the PMF. That's part of what we have to have for expected payout, right? Okay, cool. It tells us that the policy pays nothing for the first snowstorm, but it'll pay $10,000 for each one thereafter, right? Till the end of the year. Which I'm not going to worry about the until the end of the year part. All right. So how many payouts will they have? If you have X snowstorms, how many payouts will actually happen? X minus 1. Good. They'll pay $10,000 for each one after the first one. So what's the amount paid out for X snowstorms? Each one gets a payment of $10,000. Yeah, I'll just write it 10,000 times X minus 1. Yeah. So this is the function that we want to use to find the expected value of. Okay. So we'll take that 10,000 times X minus 1 and multiply it by our PMF. Where should I start the sum? Yeah, I better start it at 1, right? Because otherwise this bar is going to be negative, yeah? So I better start it at 1. I could actually technically start it at 2, but and it has to go to infinity. I'm going to do an expected value for a Poisson, right? That looks ugly, doesn't it? It's not too bad, though. Okay. First thing, any X's? Any X's? What do you think I'm going to do with those? Take them outside. Good. Yep. Take it behind the woodshed. No, wait, that's not it.
Wouldn't it be 1 to 364 or 365 about infinity?
Technically, yes, but this will be easier to do. I really don't want to do it to 365. I really do want to do it to infinity, even though it seems like that would be harder. But yes, you're right. Unless you want to say, well, I could have 2 snowstorms a day. One started in the morning, one started in the afternoon. Right? Or I could have 3. One's in, we'll have one at 8 a.m., then one at noon, and one at 4. Climate change. Okay. All right. This seems ugly. I agree. Looks nasty. And if you were doing this from a practical perspective, you would probably just take it. You would probably do. This is a very, very applied mathy type of thought. I'm going to get the exact value of this, but in practical purposes, eventually these terms are going to be super duper small, right? Because this thing goes to infinity way faster than this thing does. So eventually, this is going to make this whole thing not add hardly anything. So what I would do from a practical perspective is I'd put this sucker in Excel. I would copy down a bunch of things. And then when the decimal stopped changing, I would quit. Let me show you what I mean. And then I'll come back and actually do the exact value. Because practically speaking, you would want a number, right? If you're doing this as a business, I don't care about something in terms of e to the x. I want to know what's the dollar value I'm expecting to pay out in this policy so that I can charge a premium to enough people to sell the policy to so that I make money, not lose money. That's the bottom line, isn't it? The whole point why you would do something like this. Or the whole reason why an actuary would do something like this. You may not personally do that. All right? So what did we say that function was? It was 10,000 times x minus 1 times 1.5 to the x over x factorial e to the minus 1.5, right? That was the function I was writing up there so I don't forget what it is. All right, so if I were going to do this, if I put in 1 for x, that's 0, right? Okay, so I'm going to start this with 2, I'll do 3, and then I'll come down and copy it down in a minute. I want to plug 2 into this function, right? That's the first thing I want to do. So I would do this as 10,000 times that cell minus, I should have done one other thing, minus 1, and then multiply that by 1.5 to that cell, right? And then divide by, there's factorial built in here as well, of that number, right? And then multiplied by exponential is built in here as well. EXP gives exponential. Negative 1.5. That's what I get when I put it in 2. Yeah, okay. So do the same. I can copy this down here. Boom. Why did you give me the same answer? Give me the same number. Well, let's see what happens here. If you've got a pattern going and I pull, it'll just keep the pattern going. Here, I copied this down. I better not get the same number. There we go. Now it's getting smaller. Right? Okay. All right. So I want to add these up, right? What do I want to add? Basically, I want to take this and add it to the previous one, right? Actually, I'll do it this way. Let's do it this way. I'm just going to copy this one over, and then I will add this to the previous total, and then when I copy down, it'll total it. Okay. So if I copy this down, now I'm getting the total. And look what I said about decimals not changing. If I take, let me copy a few more of these down. If I take this and pull it, notice my decimal's not changing. That's what I meant by the decimal not changing. So I would expect that the expected value is $7,231.30. That's what I mean by the decimal not changing. If you were doing this from a practical perspective, you do this with a computer program pretty quickly, right? Let it iterate through until the numbers get close enough and then quit. Right? Okay. All right. So that's what I mean by a practical perspective. This is a very, very applied mathy way to think about it. I've got a number that's close enough, I quit. Okay. The other way is the very, very pure mathy way about it, which means find an exact value. Guess which type of mathematician I am? I'm a pure mathematician, exactly. We're going to do an exact value. Okay. Okay, how do I get an exact value? Yes. Oh, I factored it out. Thank you. Yep. Yeah, I don't want that there. Was there one there? I don't see it. Okay. I don't know. Good. Great. We're all on the same page. Fantastic. All right. So remember our Maclaurin series. Remember our Maclaurin series for e to the x is, that was 2 then, right? Mistakes. Was it 3? Oh, crap. I'm ahead of schedule. I better be careful. I left over 3. All right, so remember our Maclaurin series. I better be careful here. X to the n over n factorial. I'm getting nervous. I'll go over my 3.5 average. I need to try to lower my average. All right, that's our Maclaurin series, right? Okay. I'm going to try to make this series look like that. Okay. All right. Well, how am I going to do that? Well, the first thing I'm going to ignore this number in the front and just play with the series. Okay. So first thing I'm going to do is I'm going to split it into 2. I just distributed it and then broke up the sum. for what I just circled in red, what does it look like we did? Ignore the summation in particular for the time being. What does it look like we did?
Shifted where the X starts.
Well, I'll take care of that in a second. Well, what is it? If I ignore the summation, what looks like what happened? You're right. There is a problem with where it starts. Yeah, it's put 1.1. It's put 1.15. Put 1.5 in for x, right? Okay. So this should involve e to the 1.5, right? We put in 1.5 for x, but I also noticed my value doesn't start at 1. It started at 0. It starts at 1, right? Okay. So if it started at 0, the value would be e to the 1.5. That's if it started at 0, right? But it doesn't. So what would I need to subtract off to keep everything equal? X equal to 0 term, right? What do you get when you put 0 in for x? 1. So that's what the second one adds up to. All right. If this started at 0, we would get e to the 1.5. Right? If it started at 0. It doesn't. It starts at 1. So I need to subtract off the first term that we left off. So e to the 1.5 minus 1. That part okay? All right, let's look at the second part. I got an x here. Do you see anything I can do to simplify? Yeah, I can cancel it in the bottom, make it an x minus 1 factorial, right? Okay. Again, I still want to use my Maclaurin series, okay? Now, in this case, we will re-index because I think it'll help a little bit. If I want to make this series start at 0 instead of 1, what would I need to do with all my x's on the inside? Add 1. So I get 1.5 to the x plus 1 over x factorial. Right? We agree? Okay. Compare it to your Maclaurin series. What's different? There's an extra 1.5. How can I handle that? Yeah, just factor it in front, right? Because I can write it as 1.5 to the x times 1.5, right? So now I've got 1.5, times e to the 1.5. So I've got 1.5 times e to the 1.5. The other pieces are a minus e to the 1.5 and a plus 1. So you get 0.5 e to the 1.5 plus a 1. I'm going to take that number, plug it back in up here. Yeah. If I distribute, I can write this as 5,000. That's what that first piece will be. And then plus 10,000 e to the negative 1.5. Does someone care to plug that into their calculator? Rio, is that what you said? Hey, look, we got the same number. Phew, I didn't make another mistake. Okay. All right. This is the exact value, and then we got to use the calculator to get an approximation again. That okay? Fun playing with the chlorine series. But anyway, is the setup okay? I mean, really, again, for all practical purposes, if you were doing this as someone working in actuarial science, you would get to this point and you would put it in something that would approximate it. You would never go through the rest of this from a practical purpose. Okay. All right. Questions on that at all? Feel good about doing Poisson problems? You feel like being done 7 minutes early? Okay, let's be done 7 minutes early then. All right, have a good weekend. We'll see you on Tuesday. We'll start continuous distributions on Tuesday. You'll notice that the last couple of problems on the homework assignment I gave you were about continuous distributions, so we'll get those started on Tuesday. All right, have a good one, everybody.